learning derivatives is not just, to torture you. That's a happy side effect. But, yes?
Are we going to be writing the notes today?
Did I not hand them out?
That's why
Oh, that's why I have so many of them still left. Derp. Yeah, I have like 8 of these. I think I gave you one too many of those. Yeah. Thank you. So counting is not so good either. Man. Let's try this again. So the whole point of doing derivatives is to be able to make applications. One of the easiest ones is velocity, but we'll do other rates of change as well. So the instantaneous rate of change of a function, f, with respect to x, at a, is the derivative, f prime of a, if it exists. So mostly what we've been doing is looking at this graphically. Graphically, the derivative at a is the slope of the tangent line, or the slope of the curve at a. But in the broader context, outside of a graph, it's the instantaneous rate of change of the function. And if that function actually represents a real thing, then we have something interesting that we can talk about. For example, if a is the area of a circle, find the rate of change of a with respect to the radius r when r is equal to 5 centimeters, and use correct units. So, we know that the formula for area is pi times the radius squared. If I'm taking the derivative of a with respect to the variable r, pi is just a constant, so I keep it. You keep constant multiples, times the derivative of r squared, which is 2r. Interestingly enough, you recognize that? What is it? Circumference. The instantaneous rate of change in the area is its current circumference, which when you think about it makes sense. If you're adding on just a tiny little bit to a circle, you're just expanding it just a little bit. You're like adding another layer around it. Okay? So we want to know at r equals 5 centimeters, so dA dr evaluated at r is equal to 5 centimeters is going to be 2 times pi times 5, so it's 10 pi. Oh my goodness. And the units, notice it's the change in area over the change in radius. And the units were centimeters. That's square centimeters per centimeter. Is it correct to say centimeters is the units? Yes. Is it very descriptive? No. It doesn't tell you what's going on. This tells you that the area changes 10 pi centimeters, square centimeters, every time the radius changes by 1 centimeter. Okay? Questions about that? Cool. Let's move on then. This is partly why you're not writing the notes today. It's a lot of writing here. Okay? So one of the things that we're going to do as an application is motion along the line. So you've got an object moving along a coordinate line. Frequently it's the x-axis, but it could be the y-axis. It could be, any other line, horizontal or vertical. So that we know its position s on that line as a function of t. So s is equal to f of t. So something you studied in physics at some point, the displacement of an object. You guys all remember that? Some of you yes, some of you no. Displacement is just the amount of change. It started in this place, it ended in this place. That's the displacement. So that would be the change in s, the change in position. So f of t plus delta t, that's its ending position, minus f of t, that's its starting position. And then the average velocity, v sub average, is the change in s over the change in t. So f of t plus delta t minus f of t over delta t. And you're like, that looks a lot like something we have been doing over and over and over again. What does that look like? Limit. It does. And what is that?
F of x plus h minus f.
Oh, what is it that finds? It's the definition of the derivative. Okay? What's missing is the limit. Okay? So, oh, well, this is an average rate of change, not an instantaneous rate of change in the velocity. So this is, I went 100 miles in 2 hours. What was my average velocity? 50 miles an hour. That's what we're finding here. This is not a calculus thing at all. But if we take the limit as delta t goes to 0, now we've got the derivative, and so now we have the instantaneous rate of change, which is what differentiates calculus from prior math classes. Now we can find instantaneous rates of change, which we couldn't find before. All right, so again, lots of writing here. You may want to read over these again at some point. So when an object is moving forward, that is when s is increasing, the velocity is positive. And when an object is moving backwards, that is s is decreasing, the velocity is negative. Right? That intuitively makes sense. If we're interested in how fast an object is moving without regard to the direction, we want to know about speed. Speed is simply the absolute value of the velocity. So speed we can think of as absolute value of velocity, or the absolute value of the rate of change in position with respect to time. This ds dt is the rate of change in position with respect to time. It's the derivative of s with respect to t. Now, the rate at which a body's velocity changes is its acceleration. Acceleration is the derivative of the velocity with respect to time. Acceleration is how fast is the velocity changing over time. So acceleration at time t would be the rate of change, the instantaneous rate of change of velocity with respect to time. And so that's the second derivative of the position function with respect to time. Okay? You can do the third. I think we'll talk about this later. It's called jerk. Because if you have a sudden change of acceleration, think about it if you're in a vehicle and the acceleration changes suddenly, you feel it as jerk. And I don't know, after that it gets, there are things, but they don't make any sense to me after that. I'm like, okay, I don't really understand that. All right, I know I've made this really small, but you can read your page if you can't read this. So a particle moves along a line so that its position at any time t greater than or equal to 0 is given by this quadratic, where s is in meters and t is in seconds. So first question, find the displacement. Again, this is not a calculus question. This is just the displacement is going to be s at 2 minus s at 0. So substituting in 2, and I'm going to do this in my head, that's 4 minus 8 is negative 4 plus 3 is negative 1. Minus s at 0, that's pretty easy, is 3. So it's negative 4. So let me look at something real quick. Did this say we were on an x-axis, or it just said on a line? So it's moving in whatever is the negative direction for that. Okay? Find the average velocity during the first 4 seconds. Okay, so the average velocity is going to be, well, how much did the position change over how much time has elapsed? Just like you went 100 miles in 2 hours, you averaged 50 miles an hour. So this is going to be S at 4 minus S at 0 over 4 minus 0. S at 4, again, I'll just do that in my head, that's 3. S at 0, also 3, over 4 is 0. And I didn't put my units back here. This was meters, and this is meters per second. And you may be going, how can the average velocity be 0? Well, if I start and end at the same place, my displacement is 0, so my average velocity is 0. When you swim a lap in a pool, your average velocity was 0. Your average speed was something more than that. Okay? All right, next, find the velocity of the particle when t equals 4. So I need to find the velocity equation by taking the derivative. V of t, and you don't have to write this next part, but I always do, is S prime of t. I let everybody know exactly what I'm about to do. It's a good way to communicate what you're doing mathematically. So that's 2t minus 4. So V of 4 will be 2 times 4 minus 4 is 4 meters per second. Next, they ask us to find the acceleration of the particle when t is equal to 4. Well, the acceleration is the derivative of the velocity, it's the rate of change in the velocity. So that'll be v prime of t, which is 2. So a of 4 is 2. This has an acceleration of 2. 2 what? Well, here's where physics and I have a disagreement. It's not a strong one, but this is the rate of change of acceleration, right? I mean, acceleration is the rate of change of the velocity over time. Velocity is in meters per second. So I always write it this way, meters per second per second. In physics, most of the time they'll write that as meters per square second, which makes sense, but it's also stupid at the same time. Because what exactly is a square second? It has no meaning. But when you write it this way, it's like, how much is the number of meters per second changing every second? So then it has some meaning. I can remember as a student, way back while the earth was still cooling, that I hated it. I was like, I didn't understand. I was like, what? I understood it, but it didn't make sense to me. And now I know why. It took me 30 years or so to figure it out, but that's okay. All right, at what values of t does the particle change direction? So, here's an important thing for you to know. The particle changes direction when velocity changes sign. The velocity has to change sign. So the velocity, what was the velocity equation? Was it 2t minus 4? Yes? Thank you. Sorry, I had to erase it to move this down. Well, in order for the velocity to change sign, since this is a continuous function, it's got to go through 0. That's the intermediate value theorem. So I'm going to set that equal to 0. Solve that, which is pretty easy. That's t is equal to 2. And on this one, it's pretty obvious that there's going to be a sign change because it's a linear function. Anything that's not linear, you need to check to make sure that it really did change signs. Because it's possible that, like you pulling up to a stop sign, that the velocity was 0 and then it kept going in the same direction. Right? Just because the velocity is 0 doesn't mean that it changes direction. It means that it has an opportunity to change direction. Not that it necessarily will change direction. Right? You really can't change direction unless you're stopped for even a millisecond or something, right? Brooklyn's thinking about that really hard. You all right?
Mm-hmm.
Okay. All right, last one. Use parametric graphing to view the motion of the particle on the horizontal line y equals 2. I'm going to show you how to do this. It's actually kind of cool. Grab your calculator. You need to change your calculator into parametric mode. Several of you had your calculator in parametric mode. You must have been doing parametrics at the end of the year in pre-cal, yes? Where you have an x equation and a y equation separately? There were like 3 people who had their, and couldn't figure out how to get it out of parametric. Okay, that's fine. All right, so I'm going to make it move in the x direction. What was my equation? Was it x squared or t squared what?
T squared minus 4t plus 3.
Thank you, ma'am. And then what I'm going to do, instead of putting it on the x-axis where it's really hard to see, I'm going to put it on y equals 2. So it'll be up above the x-axis so I can actually see it. And I'm also going to do this. If you move all the way over to the left, you can change what kind of line it's drawing. I'm going to change this not to a thick line, which would be okay, but to the third one, which has a little floating dot so you can watch it as it moves. Okay, so I'll do a zoom standard here. So it should look something like that. If you want to watch it again, unfortunately, it won't redo it unless you do something. So if you just add 0 at the end and say, okay, now graph it, it'll graph it. Everybody watch the screen for this one real quickly. See, it started over here and it's moving left. It slowed down to a stop and changed direction. We said that it changed direction at what time? T equals 2. I'm going to trace this, and this is tracing, and I know that it's moving left even though I'm pushing the right button because t is what's getting bigger. As t gets bigger, it's moving further to the left, and you can see when it gets really close to t equals 2, it's all the way over here on the left. And then after 2, it's now moving to the right. It changed directions at that point. So this is how it's moving along the line. It moved to the left, stopped, changed directions, and moved to the right from then on. All right. I don't know why I didn't just do some sort of page break on this so that I could have each one of them. It's just dumb. All right, so let's see. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second so that it reaches a height of s equals 160t minus 16t squared feet after t seconds. By the way, this negative 16t squared, that has to do with acceleration due to gravity. Okay? That's what affects this. If there was no gravity, then it would just continue going at that speed forever. How high up does the rock go? Well, I need to find the maximum height of the rock. Well, what happens when the rock reaches its peak? It changes direction. Oh, I need to know, where is this changing direction? So in order to know that, what do I need to know? I need to know the velocity. So the velocity, v of t, is 160 minus 32t. And I want to know where that's equal to 0. Again, knowing where it's equal to 0 is not enough. We need to know that the sign actually does change. But since this is linear, it's pretty easy to see that it does. Just keep that in mind. Very few things are going to be linear in the long run. We're doing that because it's easy here at the beginning, but real soon it will not be. So that's going to be what? T is 5. So t is 5 seconds. So what is the velocity of the rock when it is 256 feet above the ground on the way up? Yes. Did you do something wrong?
Do we have to find how high the rock goes at 5 seconds?
Oh, yes. Thank you. So now I need to know what is S of 5. So it's 160 times 5 minus 16 times 5 squared. Let's see, that's negative 400 plus another 800, I think it's 400 feet, if I did it right.
Did.
Thank you. Appreciate you guys checking me. All right, so now, what's the velocity of the rock when it's 256 feet above the ground on its way up? So that means I'm going to have 256, the position, is equal to 160t minus 16t squared. I'll bring everything to the left so that I have a quadratic that's equal to 0. This has been cooked so that it'll factor easily. Factor out the 16 first. If you don't do that, good luck factoring this. So it's 16 times t minus 8 times t minus 2 is 0. So t is equal to 8 and t is equal to 2 are our two solutions. Which one of those is on its way up?
8 or 2. Sorry.
Why?
Because at 5 seconds it changes direction.
Yeah, at 5 seconds it changed directions and started coming back down. Right? So it's got to be at time t is equal to 2. So the velocity at time 2 is 160 minus 32 times 2, which is, let's see, that's 64, so that's 96 feet per second. Makes sense, its velocity is positive, it's on its way up. All right, wants to know the acceleration of the rock when t is greater than 0. Acceleration is simply the derivative of the velocity, and the velocity was 160 minus 32t, so that's just negative 32 feet per second. And that is acceleration due to gravity. For an object near sea level, ignoring wind resistance, acceleration due to gravity is negative 32 feet per second. When does the rock hit the ground? Well, I'm going to cheat on this. We could go through the whole thing and figure out when this is 0, Or we could just go, well, it took it 5 seconds to get up. We're ignoring wind resistance. How long is it going to take it to get back down? 5 seconds. So t is equal to 10 seconds. Yes,
Where did the 32 come from? MC.
I took the derivative. Sorry, I didn't show it. I took the derivative of the velocity function. Cool? Okay, I think that's it. Yeah.